Hello, thanks for showing up for our second portion of Turbo-Satori webinar on advanced analysis. Today we'll be speaking with Michael Lührs, and he will go into some of the specifics of the software. To start us off, Patrick Brits will take over.
Thank you. That was a quick introduction. So very happy to have you here. I should introduce you properly. Dr. Michael Lührs from Brain Innovation, person behind the software, behind the commercial software, actually a company that makes software for, mostly known for their fMRI software, Brain Voyager, that sometimes you want to focus on. You don't want to be an expert on that. You don't want to find somebody who can program, and you want to have somebody where you can ask as many questions as you want because you have a dedicated support and they're just there to help you. So you get the software, you know that it's developed to some industry standards, and you know that there is somebody that is paid for to help you. And this makes just the environment that allows you to focus on your research. And we believe that is, in some circumstances, the right thing to allow you to focus on your research. And that makes me so particularly happy that we are having the opportunity to work with not only a commercial software, but somebody who has tons of experience already in the field of this type of signal processing. And that, yeah, Brain Innovation went into NIRs data and allowed all the NIRs community, the fast-growing NIRs community, to have such a powerful and intuitive tool. I'm very grateful for that. So with further ado, Michael, all yours. Thank you so much for being here.
Thank you very much, Patrick, for this nice introduction. Yeah, I would like to begin with a short outline of this webinar. So we will start with a brief summary of Turbo-Satori Webinar 1. So for those of you who've missed that, we'll just shortly go to the steps, showing the software and what you can do with it. Afterwards, I will show you some examples of BCI application that you can do with Turbo-Satori. And one of the most interesting questions, I think, is how you can access the data. So if you want to set up your own experiment using maybe your own presentation software, how can you get the data from Turbo-Satori? And yeah, afterwards, I want to talk about the quality control, which is another important thing that you should do for offline experiments and also for real-time experiments, because then you could take actions during the experiment and not just seeing later on that maybe your data is corrupt or something went wrong. And yeah, at the end, I want to talk about multivariate data analysis in Turbo-Satori using support vector machines. And the final thing is, of course, the question and answer section. Okay, so let's start Turbo-Satori. If you start the software, you basically have two options, the real-time and the simul mode. The last webinar, we mainly used the real-time mode. Today, because I don't have a device connected, I will focus on the simul mode. It's basically simulating data analysis from an already acquired data set, using NIRScout, NIRSport 2 or NIRSport devices. And yeah, you can just click on this button and then it will load the application. Now, the first window that you see is maybe a bit comprehensive in the beginning, but you have all the options to basically reduce the views and show the information. But to fill them with some content, we just load a data set. So we just click on Start and select some example data. And here you see what kind of data can be loaded. Turbo-Satori supports at the moment .hdr, so .header from NIRx. Then it also supports .NIRS and our own file format, which is .sri. In the future, there will also be .sfNIRS file format covered, which will be in the next couple of releases. Right now, we stick to the .hdr, so we just click Open. And basically now Turbo-Satori will read in the data. What you can see as soon as it's starting reading in the data is this vertical line, which tells you where it currently is accessing data, as well as here in the packages. And now you already have control over the whole user interface. So you can minimize a bit the viewports towards the information that interests you, for example, the screen that you want to look at, and can select channels and look at the time course of these channels. And this you can just by clicking on this channel or using the channel selection bar. And what we nicely saw last time is if you select a channel and use the neurofeedback experiment, that you can use this as a neurofeedback paradigm. But here in the background, we see the green and blue conditions. And just to make it a bit more clear, so the green condition is left tapping and the blue condition is right tapping. So we also give some information to this. And if you now want to see what is going on during this information, you can use the real-time statistics, which we were talking about last time, but just defining here a little plus, and then you would see immediately the statistics. So in this case, the beta values. And it might look a bit too strong at the moment, so you can just increase the threshold, and then you get easily a nice view of the beta amplitude. And you can see already after one trial for the left tapping that you quite nicely form a specific cluster in the right hemisphere, as you would expect. Now, if you want to look at the second condition, which is right tapping, you can basically change this from plus to minus and completely remove it and just set a plus here. And what you see immediately is that the amplitudes seem to be quite low compared to the other side. So you just use thresholding here, and then you see, okay, but the pattern seems to be available as well. Now, this t-statistics is basically something that tells you, is there something statistically comparable to my predictors? So if you want to look at your predictors, you just click here in the show href button, and then you see for each of the tasks how your expected model look like. If you click on the t-statistics, so just change back to the strong reply, you basically see the statistics calculated for this specific contrast, which is now just left tapping. And also here you can change the thresholds, which will then have an immediate effect on the color coding here, as well as the color coding here. Now, if you want to see which one is the strongest channel, you can just use the sorting, double-clicking here in this field, and then you would see basically immediately which channel seems to have the strongest or highest t-value, and just by double-clicking you can disable this one as well. So this is the main framework for the statistical part. You can also do contrast when checking if there is any channel which has a higher t-value compared a higher amplitude comparing left versus right tapping, and specific questions, but this will be covered in a later step. Okay. So everything that we will basically talk about is also published in an open journal. So you can just look at more detailed information online in the Neurophotonics journal. But of course, current updates and features that were added, they are always described in our users guides. So just check out our support website for the users guide or use the users guide within the software. I was shortly talking about neurofeedback applications, as you saw in the first webinar. So the main idea is that you present to the participant or patient the information of their brain activity. And this can be done using, for example, a thermometer, or, which I will show you later, are different BCI examples. Now, how does this work? First of all, I can start the BCI demo, which is just a little application which can, for example, show you the thermometer feedback. And I want to connect this now to Turbo-Satori. And you see here that the color bar here is yellow, meaning that there is no connection. As soon as I start Turbo-Satori in the simul mode again, basically see that here the thermometer turned on. And now as soon as I start the data analysis, you can basically see that by selecting a channel, the color coding changed to green. So there's an immediate connection between these two applications. And since the software Turbo-Satori is telling in a broadcast manner that it is available and someone can connect to us, the BCI demo here is connecting automatically and you don't have to do anything. By switching between channels, you basically change the input for the BCI window, and by this you can control for different inputs. Now, if you want to use a different example, for example, a flame, which shows you the amplitude of the signal, you can just switch between them. And yeah, what you will see as soon as the signal will rise, which you can see here, zoom in a bit more. You can basically look at the flame and should be able to see that this signal is directly coupled to the signal over here. So you see the increase here, and basically the flame is also increasing in the same manner. There are some more examples which you can use to get started and to try some things within the software, which are, for example, the thermometer which I showed, but there's also a little breakout game where the movement of the pedal is coupled to the signal here. So the goal is for the participant to basically hit the ball at the right time and the right spot by changing the amplitude signal. This software is also available on the support website, so you can just download it and play around with it. So how does this connection in general work? So we have this framework that you might know already. So we have our data acquisition software, which is NIRs or Aurora. Turbo-Satori will connect the software using the lab streaming layer connection. So as soon as this connection is available, the data can be received in Turbo-Satori. And to access the data from any stimulus application, you can use a network interface, which we will provide. And we have some example of this network interface in Python, MATLAB, and C++. And I will show you in the next step how you can access the data. After this is done, you basically present the information to the participant, and this will then influence the signal itself. Now, one example BCI application next to the Neurofeedback is coming here from the group of Bettina Sorger, where they basically used temporal encoding of brain activity. As you can see here, at specific points in time, a specific task is performed, and in another paradigm, also from the same group, you see that this can even extend it to 5 different time periods, which can be used to encode specific decisions. Now, how does this work? At a specific point in time, the participant is asked to perform a predefined task, for example, motor imagery or mental calculation. So in the mind, and he should start this task as soon as a specific option is shown. For example, he should start if the letter A is shown, and then he should stop as soon as the letter B is shown to indicate, okay, I wanted to choose the option A. And the same is true for all the other options. And by this, using this temporal encoding, the participant can easily point out which choice you want to make. This is integrated in the software as well. So we have a BCI dialog, which basically does this whole computation in the background and will point out all the information for these specific decisions. And this was done by Bettina Sorger and her group, and we developed this part in collaboration. To show you how it works, I start the software again, and I basically only select the BCI dialog, in this case the 4-choice paradigm, just to show you how it works. So here you see the paradigm, and we already saw that that we have a specific channel that gives a good signal. Now I decoded the choices, so we don't know which choice this specifically is. And just by selecting the channel that we know should have a good signal, we can provide input to the dialog over here. Now we increase a bit the read-in speed because it would take a bit more time. And you'll just use this wheel here in the top. And as soon as the condition is is done, the calculations will be performed in this window. And what you can see is that for each of the possible responses A, B, C, D, there will be an individual plot helping you to select which one seems to be most promising, and also different statistical values are available. I won't go into detail in this, but if the majority of the possible decisions match, as you can see here, so this is the sum of the small decisions here, you can clearly see that the decision in this case was the letter C, which is also pointed out here. To continue the reading, basically go to the next trial, and after this trial you will also see the next time course over here and the possible decision. Of course, we can use the interface over here to do the statistics as well. And there we also see that the letter C seems to be promising. If we look at the condition 2, we don't see any response. If we look at condition 1, we also don't see anything. So with this, it's really easy to just use the contrast as well to have a clear decoding. These decisions can be then exported to a file and just read in from another application to make a decision or to create a BCI. Quality control is a very important part of fNIRS data analysis because you need to know during your acquisition if your data is good, so that you can maybe repeat a session or even stop a session that is currently going on. Now, there are multiple options within Turbo-Satori that allow you to do this, this quality control. It includes heartbeat detection, contrast, event-related averages, and yeah, some other features, but we will go into this in detail. So looking at the interface, we have for the real-time contrast, as I used already quite extensive, the possibility to have specific contrast, so checking if the participant is doing the task that we ask him to do or paying attention to the stimulus. So this we see in the view over here and in the activity over here. Next to it, we have the overall channels. So this we can use to inspect for motion. And here we, for example, see that this is basically more or less a flat line. So there's no motion in the channels. But if we would see a spike, it would be visible in this plot right away because we have all the channels plotted at the same time. Then we have the event-related averages. Looking at this graph only might not show you the information that you are interested in detail. So using this, you get the error bars as well as the mean signal. And this can clearly give you an idea if the participant is performing the task, but also if he is performing it on the same level each trial. And over time, it should be yeah, smaller error bars, and it should be a more consistent signal. The heartbeat detection is visible in using these little icons, so these heartbeat icons. If there's no heartbeat, this would be basically an empty circle. But you also see the heartbeat here in this bars, and this we also showed last time in the webinar 1. But just to recap, that this is also available here. Next to these measures, there is the anti-correlation. The calculation times and the anti-correlation. The calculation times are important to see that your hardware is yeah, doing the calculation fast enough. So you see the calculation times, and the plotting times can be that your graphics card is not strong enough or your PC is doing something at the same time. So you can just look at these times over here to check if this is still okay. Turbo-Satori will automatically reduce the amount of plots that it's performing if the plotting time is too long to avoid any delays in the processing. Then the anti-correlation basically shows you if oxy and deoxy are anti-correlated. So what you expect is a blue signal, and this we see for the majority of the channels, which you can see here in the spectrogram plot. But for one channel here, in this case 8.8, you also see, okay, there's the anti-correlation not as high. Could be due to motion or not a very good connection of this optode, but you get this information right away and all the details. And another important option is to look at the frequencies. So you have some expectations what signals should be in your HBO or HBR data. And by just switching from layout to frequency, you can inspect which frequencies are present in your filtered or unfiltered data. In this case, you would have a task frequency that you would expect, for example, here or here. And this is updated in real time using a window of 2000 data points if possible. Okay, from the data quality, I just want to close the loop, going back to the data acquisition. So how can you access the data from Turbo-Satori? And I think most of you will use either MATLAB or Python as their programming language. So I just want to show how this works in Turbo-Satori. So first we start again the software. And we load a data set, same that we loaded last time. And this time we don't do it in the slow way, we just fastly load it. You can switch to fast mode by just turning this wheel to the maximum, and then you see that the data will read as soon as possible. Okay. Now we select a channel which we already know gives some promising data, and just check that all the data is available. Which you can see now quite nicely. Now we run for example, a Python script. And as you can see, the data was extracted immediately from Turbo-Satori. And as an example, you can also, for example, show the data coming in real time. So not just grabbing the whole data set, but really doing in real time, getting each frame individually. Here I show you the statistics. So you can also grab the beta values if you want. And these are basically the same as in Turbo-Satori. Now, if you want to be sure that the data is really the same, most of you might use MATLAB to access this information. And there's also an interface for MATLAB. But first, I want to show you the interface for Python. So this is basically the interface for Python. To connect to the software Turbo-Satori, you mainly use one call, which is the Turbo-Satori network interface. And all these functions are part of the experiment library. And experiment is an open source stimulus application developed by some people in Nijmegen, mainly as well Florian Krause. And he also implemented the Turbo-Satori network interface. So if you want to download it, just go to the GitHub page of experiment and download the experiment stash for more information. And to grab some details, you can have just very easy calls, for example, to get the current time point. So what time point is currently processed, you can just ask this information. Which channels are available, you can also ask with just one call. And there's a very extensive list of this. And I want to show you how this list looks like in MATLAB, because the calls are very, very similar comparing MATLAB and Python. So with the MATLAB interface, which you can download from the support website of Brain Innovation, you will find some example scripts. I just will run it for now. And this script will basically include all the functions that are available in the network interface. So all the information that you can grab from the software, for example, the predictors, the confound predictors, protocol conditions, and so on. And as an example, I show you here the same data, but doing the statistics within MATLAB. So basically grab the design matrix and the conditions. So just clean now the deoxy part so that you can see the oxy part. And as you might already can see that the signal looks very similar. So this is the same signal that we're looking at. And to check that the statistics is the same, we can go into Turbo-Satori and go to Analysis, GLM Diagnostics, and show basically the predicted signal. And as you can see, this one is the same one as we would get in MATLAB. But you also can look at these beta values here, for example, and can grab all this information. These scripts are, as I said, available within the interface, and they include also the new features which will come into the software. So as soon as there's a new release of the software with a new feature, they will be also added to the interface so that you can access this information as well. Okay. So what we were looking at till now are our individual channels. So we basically checked after a stimulus was shown what is going on in a specific channel. So here, for example, we can see that there seems to be for the blue part a higher signal compared to the green part, and here in this channel it seems to be the other way around. So the green seems to be a bit higher. But what we can't tell with the GLM or univariate data analysis, if these sites, for example, are connected, or if they interact, or if they maybe even jointly encode the stimulus. And this information can only be answered or requires multivariate data analysis, where you not only look at one individual channel at once, but look at the coupling and the combination of this. Now in Turbo-Satori, we integrated the support vector machine, and I want to just shortly introduce to you what is done in the background of the software. Now, if we look into the univariate way, we basically have two classes here as an example. So class A is marked in green and class B is marked in red. Now looking at one channel, we can see that for the first class, it seems to have a quite high response for the class A and quite low for class B. And if you look at the channel 2, it seems to be the other way around. So these patterns we can easily distinguish also in the univariate way, but there is a way that we can easily or make this more clear. And this is by using multivariate analysis. So we have the possibility to plot the channel 1, for example, on the x-axis and the channel 2 on the y-axis. Now, if we now would add the class A and B parts to this multivariate plot, we basically would see that the first, so the screen dot would have a very, very high response for the channel 1 and a pretty low response for channel 2. And if we look at this pattern, we see a pretty high response for channel 2 and a low response for channel 1. What you can immediately see is that there's a huge difference between these two sets, which makes it for us very easy to see the difference as well. Adding more data to this plots will make this case a bit even stronger to see. So here on the left, we have again some more points shown here for the first condition and so for the second condition. Now, if you plot these into the multivariate plot, we can see that they form a clear pattern, which is very easy to distinguish. So already just transforming from a univariate way into a multivariate plot gives us way more information. Now, what would be if we look into a more difficult case where the two conditions are not as different as we see it here? So would you be able to distinguish the two conditions? I mean, some could say, okay, there's a bit more activity in the green part here and a bit less in this channel, but you wouldn't be clearly able to distinguish. Now, if we plot them again into our multivariate session, we can see that they seem to form two clusters which are still different. Now, the main question for the multivariate data analysis is how to separate these two classes. And of course, there would be multiple options. So you could, for example, draw a line like this, which would definitely separate these two. But you could also draw a line like this, but you wouldn't really know which one is the best. So just by eyeballing, you would think that this one seems to be the best. And this is exactly what we want to figure out. Now, if you have this line and decided for this, you can basically plot the data onto an extra line over here. And this allows you to make a decision between the two classes. And I want to make an example to make this more clear. If you would add another set of points, which you can see here, which you wouldn't be able to distinguish easily, we can plot these points now into our multivariate chart. And you would see that they would end up below or above the specific line. And with this, by projecting them on our support vector, you would be able to differentiate between this first and the second class, which wouldn't be easy on this univariate way, or even not possible. Now, there are different ways to find this discriminant, but the general term is that for an input vector, we need to find a discrimination function that is basically the linear combination of x, and that can be written in this fashion. And the main idea is that if it belongs to class A, this function satisfies the following condition, and if it belongs to class B or to the second class, it's basically smaller than 0 in this case. Now, we saw this these 3 points, and what we already could show is that the difference between these two clouds can be, we can distinguish them in different ways. And the hard margin to support vector will basically ensure that only the classes that are clearly distinguishing the two lines will be used as a support vector. And the option that we used is basically ensuring that the largest margin, so the largest differentiation between the two groups, will be used to point out the support vector in that case. Now, if you have a lot of data, it's maybe not possible to have a vector which clearly separates them. So we should tolerate misclassification. And this we can do by adding this little C term over here. And this allows us to point out that we are fine with some errors in these calculations. Now, for the soft margin SVM, which allows us this, if we have a strong value for the C, so really not allowing any errors to make, we basically would, with a new point added, so compared from here, these 3 points, basically add 1 more point, you would see that this would completely change our line. If you would now change the C to a lower value, you would allow more errors. And this would allow you to differentiate this pattern in a more general way. And increasing the C or decreasing the C even more to 1 would allow you to have even a better fit between these two classes. And you can find the best C using, for example, cross-validation and some feature reduction as well. Now, the support vector machine is basically a 2-step approach. And the first, you need to train your classifier. So you need to find the support vector, which we are talking about. And this you can do by creating a training data set or multiple training data sets. So the participant is, in this example, performing a finger tapping task. We basically analyze the data and extract the labels for this specific pattern or task that we were performing. And then we feed this information into our classifier. And as soon as we've done this for left and right, basically our classifier is trained for this specific pattern. Now in the second part, we can use our trained classifier and in a subsequent session and classify what a person is doing at the moment. So it's again the same setup. So the participant is performing a task, but now the data is analyzed in the classifier, and the classifier will make a decision based on the input that he got. And in this case, for example, with this data, he would guess that the current decision was right-hand. So this two-step approach is necessary for the SVM, but with the NIRs systems, you can also make a general decision. So if you have a pattern which you see in most of your participants, you can also train a general classifier to use it for new patients that are coming in or participants. Now, how does it work, or what are the advantages of the MVPC? So weak information that are at individual locations, which we can't see with the univariate approach, can be accumulated, and this is an efficient way using the multiple locations. We can integrate weights from individual channels, and this can be learned by a classifier. It's more fine-grained spatial information, because that's also the strengths from NIRs, that we can place our source and detectors as specific locations. So therefore, we can extract this information, and we can do this quasi online, doing the data acquisition. It allows you to reveal distributions which you might not see within just univariate ways, and therefore can use this information as a more direct approach. Now, how does this work in Turbo-Satori? We'll show you here as well, step by step, how we can perform such an experiment. So first of all, we have to create our training set. So we have, in this case, 4 runs which we can prepare. And I just start this run. Preparing this run basically means that you run this whole analysis in Turbo-Satori and prepare the data so that it's possible to access this information. Now, I've done this already for the other data sets. So in general, you would just need to rerun the data, or if you do a real-time session, you already created all the information that you need. And then you can use the SVM training to load your data. So in this case, we load the SRI files, and I'm doing this in an easy way by just putting out .sri, and then I would see already the specific files. So don't use the run test, because this is our testing data set, which should be independent. Just open them, and then they will be automatically loaded into the software. And we see that we have here 2 conditions in the protocol, condition 1 and 2. This needs to be the same for all the data that we load. And we can decide which chromophore we want to use, if we use oxy, deoxy, or both. And we can decide what input should be used for the classifier. So we can use, for example, the GLM results. We can use the mean raw value, or we can even decide the measured mean response, which we were talking about last time. Extracting the data is basically done here. So we decide which length of the data we want to use, or we can use the trial duration itself, which is defined in the conditions. And you can see this over here. If you have decided on what you want to do, you just press go. And then all the trial data, so each of these individual blocks, are extracted and available here in these plots. This includes all the non-masked channels, so all the channels that you see here. In this case, we have 20 channels. So to create our training data, can just press create and look at the data over here. I will go into this plot after the training, just to show you this later on. To decide where the support vector is, we have different options, like the kernel, which I introduced to you, is now the linear one, but you also have other options to decide for the support vector. It can be RBF or a polynomial. And the C value, which we were talking about beforehand, can be defined here, but we will stick to 1 for this example. Now, if you've decided for this specific task, you can just click on train, and then your classifier will be trained. And what you see here is for each of the trials, so for each of the repetitions which we have, we will get a classification value. And overall, our classifier has an accuracy of 100% for this data that we used. Now, looking at this plot, we can basically see all the extracted data. So we look at these specific channels, so 1 to 20 channels, and we look at each condition. So this is condition, the first condition for the first data set, the second condition, so condition 1, condition 2, first data set, condition 1, condition 2, second data set. So we can already see that for some channels, as you can see here, for the first condition, we have quite an active part, and for the second condition, we have quite a low part. This is here in the bottom is shown as an average, and there you can see that there is a pattern within this, which is a good sign that, you know, okay, already extracting the data seems to have a clear pattern available. Okay, how can we use this train classifier now? We just go to Analysis and click on Real-Time Support Vector Machine Classification. And now we basically just trying to organize this a bit better. Okay. And now we basically select our classifier, which we just trained. Which is this one. I just open it, and I can see here the settings that were used for this classifier. So then I can just click on Predict, and now it's waiting for data to come in. I just make this one a bit slower so that it doesn't read the data too fast, and I run my run test, so the independent data set. So this run test can also be, or is supposed to be a real run, so in the real world, and not an offline one. But for this webinar, we just use the offline way. So now you see that the data is coming in, and the classifier is now using the trial duration to predict the specific condition. So it can increase a bit the speed. So after the condition is done, the classifier points out a prediction, and the prediction value is either positive or negative. For the first condition, you expect a positive value, and for the second condition, you expect a negative value. And in this case, for this specific condition, which is 2, so this is condition 2, 3, because 1 is in this case rest, we get a positive value. Let's continue the data analysis. So now the second trial is over, and what you see is that for the second one, you get a strong negative value, meaning that this one is condition 2, or condition ID, including the rest condition is in this case 3. So what does this predicted value mean? The support vector, what I was talking about, is had this specific margins, and the margin of this vector is basically the value 1. So if there is now a condition which is close to 1, it basically shows that this is basically close to the margin. If the value here is pretty low, it's basically very close to the support vector. So it's a very uncertain value. So the higher the value here, the more certain, or the more away from the support vector it is. Okay, so now we can let it run through a bit faster. And since we switch between the two conditions all the time, you would expect also a switch over here. And you can nicely see that it always switches between positive and negative value, which indicates that the classification in this case worked quite well. So this information can also be accessed in MATLAB and Python via the network interface. So you can in real time ask for the predicted values for the current classifier and for the output, and use this value right away to build your BCI. And we can do, of course, while this is performing, we can also do the statistics. So we can check also over here if we would also get some patterns in the univariate way. And what I was doing right now is setting, is there a channel where the condition 1, so the left tapping gives me more or a higher activity compared to the right tapping. And what you can see is that this contrast is true for the channels on this hemisphere, and also gives you a negative response on this side. If you also want to include that that this is also ensuring that we have a positive response, meaning that our signal goes up and not just down, we can add another contrast here, and then we can do a conjunction analysis and basically include both conditions. So one that the left is bigger than the right tapping, and the second one that the left tapping is also positive. In this case, it didn't really change that much, but with this you have a combined way of looking at it. So this was the support vector machine part. I just want to shortly summarize what we have learned till now. So the software is quite flexible, and you can adapt it to your needs. So you can adjust the interface as you like it. As soon as you close the application and start it again, it will basically keep all the information that you had just chosen. So the windows and the setup that you used, and you can just start with the same settings again. So just run the same data here, and using this wheel, running it fast. The requirements to run these applications are pretty low, but it depends on the amount of channels that you want to use. In this case, 20 channels will be no problem at all. If you have bigger designs, 128 channels or more, yeah, you have to take care that there's enough processing power, enough CPUs and available. But you can, of course, hide specific parts like this plot. You can hide completely, which will decrease the load for the software. If you want to get some more information, you can just go to Help and Users Guide. In here, we have more details about the GLM, the general linear model, for example, how it is calculated, what it basically includes. And yeah, so you can check this out for more information. We also have a search and easy access functions, but this Users Guide is also available online, as well as the classification is described here in detail, so you can really get all the information that you need. And if you want to have access to this data, you can also just download it from the publication of the software. Yeah, with this, I want to thank you for your attention, and yeah, I'm there for questions and hopefully try to answer them.
Okay. Thanks so much. I'll open this up to questions now. I do apologize. I should have given a little bit more instruction at the beginning of this talk. So if you have any questions that you jotted down, please send them via the chat box that's within the menu. So we have received a few, and there's a number of questions from last week that we ran into some IT problems with. Those we will address independently in email response. But moving forward, the first one on our list here is, can a single PC handle both data acquisition, so NIRstar, Aurora, and the BCI computations of Turbo-Satori in real time? And if so, would that be suggested?
So in general, you can use one PC to do both recording and calculation. Yeah, you should just take care, as I said, that in Turbo-Satori that you see the calculation times that are available. The computations that you see here, especially the t-test, is quite extensive because it's running in the background a full autocorrelation correction. So this is a full GLM that is done for the t-test. So this can be quite extensive for the computation. But if you don't need the t-value in real time or online, then you can just switch to beta, and the computations will be much faster. And yeah, so if you have this, you can just perform it, and it shouldn't be a problem. But the most important is that you check in advance using your setup if there's if this is possible or if this is a problem.
Okay, thank you. The second question is there an LSL stream into Turbo-Satori to catch the stimulus timing in real time, or does this have to be predefined?
So the LSL stream is not available from Turbo-Satori. So you have an LSL stream from your application to Aurora, which ensures, or NIRs, which ensures that the triggers are sent directly to the system, which will then combine them with the frame. So in general, Turbo-Satori will get the information of you, or of the trigger that you send to the acquisition software, and use this as an input. So that would basically ensure that the frames and the stimulus timing is the same.
All right, moving along. Do you provide access to SVR coefficients or just the binary classification labels?
So currently we only use the binary classification labels that you can access. But yeah, you can just drop us an email and we can try to open up these information as well.
Great. Do you provide access to changing the C soft boundary parameter in the training step, or is it set by cross-validation within the code?
So the C value can be changed manually, so you can adapt it and then do the cross-validation and check if your if the classification gets better or worse. So in just let's see if we can just simulate it over here. Just shortly run this data set again. So if you see any delay in loading the files, it's because of Windows doing some search indexing, which can be a bit slowing down. Okay, so I just do the whole procedure again. And just ensure that I don't use the training one. Okay. Okay. Okay, go create. And now you can use the training and the permutation test to check how your cross-validation would look like. And you can now change the C value to a different number. So yeah, if you want to set it to 20, for example, just train it again. And then you would basically get the results for this specific value with the C value. So there's no optimization in that sense, but you can do yeah, some manual adjustments by just retraining with this specific C value. But if you look at your plot, you already would see some some idea how good your data could be differentiated or how generalizable it is. And this is because you have the specific patterns, maybe in some more or less of the trials. So this gives you another idea, but just one way to look at it.
Okay, great. Is the GLM implemented as incremental updates of the least squares equation, or something fancier like the Kalman estimator?
No, so the GLM is implemented as a real-time way. So the betas that you see are based on the real-time calculations, and then we run a full GLM for the t-test. So we estimate the AR values, and then we rerun the whole GLM, which is done in parallel to the whole calculations that you see otherwise, so that you can ensure that the whole processing is done in real time and the t-statistics is done online, so as soon as the calculations are done. But you can, yeah, so there's just the default real-time estimates. If you want to access this information, so I can just show it over here. You can see that by showing the predicted, for example, not this one. Yes, data demo. You can see how the prediction is performed, and this plot basically shows how your prediction changes over time. Because as more data is coming in, the more information you have. So the difference is your quality. But the closer you get to the end, the closer you should be to the final prediction. So I can just show you this in here. So at the end of the run, there will be a full GLM calculated, but you can see here right now that the difference is being smaller and smaller and it's more stable. And now at the end, there's full GLM and you get the predicted signal as you know it from any other offline calculations.
Okay, great. How do you exclude bad data, such as motion artifacts in the model, and can it be done in real time?
So you have multiple options to exclude this information. For example, depending on your layout, you can include specifics. So here we don't have a short distance channel, for example, but if we look at these channels here on the side, we can see that they are quite, they're not really related to the data, at least not much. So what we can do is we can use the GLM and include specific channels. So S44 and S88, for example. So we just click here at channel confound predictors and press OK. And now in addition, you can say use GLM filter. And this will basically result in a GLM, which is calculated based on the confound predictors, which are used here, and will clean the data using this confound predictors. So I can show you how this looks like. So you just run the data again. I'm sorry for the delay with the loading. So now you will basically see the signal cleaned with the two channels on the side. So we recommend to add a longer rest in the beginning so that the GLM calculations can settle. But with this, you are able to exclude specific information from your data if you need to. And this is basically the case for the specific channels. As soon as there is a access to the motion parameters, we will also include this one to the confound predictors, and then you can also use this in the GLM filter. Next to that, we have the motion correction, which can be used, and the SSR correction, or adding the short channels within the in the confound predictors. Currently, we don't check specifically for trials where motion occurs, so we use the filters and settings within here. But this is a plan to also integrate a real-time check for specific motion and then exclude this. So using adding predictors that are really detecting motion and adding this so that they explain the motion and can be used in the GLM filter to clean it.
Okay, great. This one actually dates back to last week's talk, and specifically about the demo that I was a part of. But could you give more details on how to optimize the neurofeedback threshold for each participant, and how you would go about doing that?
Yeah, so I can show you just an example how this could look like. So you have the option to run a localizer, which is basically just a way of getting this information. I should shortly exclude these confound. So if you have this confound channels selected, which were for another data set, you can just uncheck it. But you also see here that the channels are marked with a C. So this channel uses the confound predictor, so you shouldn't, you should expect different values for these marked channels. And you also see a little warning over here, just to not make a mistake. So using a localizer will provide you with the information that you need to decide on the on this value. Within the software, you have a scale factor over here, which you can use to scale the data between 0 and 1, for example. But you also get for each channel, of course, the beta value. And if you look at the predicted signal, the beta basically scales your predictors that you see here to the level of the signal. And right now you can see that the expected beta is 0.4, right? So that's nearly twice this amount. So if I would scale this to 200, and I would basically just rerun it. And with this, I would expect that I can scale my signal close to 1. So the general problem is that depending on the setup, on the data quality, and on the location, the signal strengths can differ across sessions and across days and across participants. So defining a specific value which is true for all is very difficult. But what you can do is you can integrate a specific trial, for example, in the beginning of your neurofeedback session, where the participant is just performing the task for a few, for 1 or 2 trials, and then you can use, for example, the beta to define your maximum % signal change. Or you run a full localizer or a small localizer to figure out, okay, is my variance within the trials low enough so that I know, okay, the participant is performing good enough, and then you can use this information as well as an input source. So these are some ideas how you can integrate it, but you have multiple options to decide on this. We also have created some plugins, or they're not available yet, but we have some plugins which calculate basically the quartiles and the maximum % signal change during the localizers, but this can be also done in MATLAB by just grabbing the data over here and just run the calculations there. So you're very flexible on how to decide on that, but I would recommend to do this individually, as we know from fMRI research as well, that also there for neurofeedback you really gain if you do an individual definition of the maximum % signal change.
Okay, thank you. So the last question, it looks like, could you show again how to use the individual hemodynamic functions as my GLM basis function?
Yeah, so the main idea of this was to have a specific time course. So this option is here requested, so the measured mean response. I shortly can go to the user's guide because I'm not completely sure if I have this, so you can just search for this response function, and here we have an example file how it looks like. So we will provide an easy function which you can just use here in the GLM tools to extract your measured mean response, which is not available yet, but then you can easily grab this. Right now you would we would need to extract this here, but we will work on this as soon as possible so that you can extract this EHRs. I'm not sure if I have an example one available, but in general it would be similar to this curve. So it will basically reflect this specific curve in the task. The thing is that the EHR will also be available for different conditions. So here you see that you have the number of EHRs, for example, 2. So you can make for each individual condition a specific curve, which you can then use. But if you're interested in using it, please drop us an email and we will try to combine this together with you to find a solution as soon as possible.
Okay. I'm just double checking to make sure there's no more questions, and that looks to be it. So I would like to thank you for giving the talk today, and everybody for tuning in. This will be on our support portion of the website for you to look at the slides and video at your convenience. Thanks so much.